Logistic test. Introduction. The logistic test, or logistic regression, is a statistical method used to predict the probability of a binary outcome, such as success, failure, or yes, no, based on one or more independent variables. Unlike linear regression, which predicts continuous values, logistic regression models the relationship between the dependent variable and predictors using the logistic sigmoid function, which outputs probabilities between 0 and 1. It is widely used in fields like healthcare, finance, quality control, and marketing to classify observations and estimate the likelihood of specific outcomes based on input data. Welcome to today's session. By the end of this session, you'll walk away with practical and applicable knowledge that can help you analyze different types of categorical outcomes using logistic regression techniques. Here's a quick look at what we're going to cover. YKDOY. 1. BLR. Binary logistic regression. We'll start with the simplest and most commonly used type, binary logistic regression. This is used when the dependent variable has only two categories, such as yes, no, pass, fail, or defect, no defect. We'll explore how to model and interpret this type of outcome using logistic regression. 2. NLR, nominal logistic regression. Next, we'll look at nominal logistic regression, which comes into play when the outcome variable has more than two categories that do not follow a specific order, such as product types or departments. We'll learn how to build models for these and understand their predictive structure. 3. OLR, ordinal logistic regression. Finally, we'll dive into ordinal logistic regression, used when the categories do have a natural order, like customer satisfaction ratings, e.g., low, medium, high. This technique helps us account for the inherent order in the data while making predictions. Throughout the session, I'll walk you through real-world examples and interpretations so you can clearly see when and how to use each method effectively. In the DI-CX category, where our dependent variable, y, is discrete and the independent variable, x, is continuous, we have three logistic regression models to choose from, depending on the nature of the discrete outcome variable, y. Let's break this down. Binary logistic regression, BLR. We use binary logistic regression when y has only two categories, such as yes, no, pass, fail, or defective, non-defective. X in this case is a continuous predictor, like temperature, production speed, or age. This model predicts the probability of one of the two outcomes and is the most common logistic model in practice. Nominal logistic regression, NLR. Nominal logistic regression is applied when the y variable has more than two categories, and those categories have no natural order, such as selecting among different product types or departments. Again, x is continuous. This regression helps us understand how x influences the probability of each y category. Ordinal logistic regression, OLR. Finally, we use ordinal logistic regression when the categories of y have a meaningful order, such as customer satisfaction ratings, low, medium, high, or service quality levels. Here too, x is continuous. This model respects the natural ordering of y, while estimating the influence of x. This gear diagram is a visual metaphor. Each type of regression is a different gear you engage based on the structure of your categorical y variable. Choose the right one based on whether y is binary, nominal, or ordinal. Let's start by understanding what logistic regression is. Unlike linear regression, which predicts continuous values, logistic regression is used when the outcome variable is categorical, specifically binary or discrete in nature. We use logistic regression to model the relationship between one or more independent variables, x, and a dependent variable, y, that can take on limited values, usually in binary form like yes, no, pass, fail, or defective, not defective. Now, what makes this technique powerful is that it doesn't just say whether something will happen, it tells us the probability of it happening, using something called the logistic function, also known as the sigmoid curve. When do we use logistic regression? 1. When the outcome variable is binary, like answering the question, will this transaction result in churn, yes or no? 2. To predict the likelihood of an event occurring based on various predictors. For example, what's the chance of a customer buying a product given their age and income? 3. To estimate odds or probabilities, it helps answer, how likely is it that X will result in YI? And finally, it's used to assess how much influence certain process variables or risk factors have on a particular result. In summary, logistic regression is the go-to model when your output is a categorical variable, and you're trying to make a yes or no decision based on several inputs. Before we apply logistic regression, it's crucial to ensure that certain key assumptions are met to validate our results and improve the reliability of our model. Let's walk through them. 1. Binary or categorical. Dependent variable. Logistic regression is specifically designed to predict a binary or categorical outcome, such as yes or no, success or failure, defective or not defective. So, our y variable must fall into these categories. 2. Independent observations. Each observation in the dataset must be independent of the others. For instance, if the same subject appears multiple times, that could violate this assumption and skew the results. 3. No multicollinearity. Among predictors, multicollinearity means that two or more independent variables, x's, are highly correlated with each other. This can make it difficult to determine which variable is actually influencing the outcome. We typically test for this using the variance inflation factor, VIF4. Linear relationship between log odds and predictors. Although logistic regression models a nonlinear relationship, it assumes a linear relationship between the log odds of y, and the continuous predictor variables. This is often checked using Box-Tidwell transformation or partial residual plots. 5. Sufficient sample size. Logistic regression requires an adequate number of observations. A common rule of thumb is to have at least 10 observations per independent variable category to ensure that the estimates are stable and significant. So, in summary, make sure your data meets these 5 criteria before using logistic regression, or else the results might be misleading. If these assumptions are violated, we may need to transform the data, remove variables, or consider alternate models. Let's now dive into binary logistic regression, which is one of the most commonly used logistic models in data analysis. Binary logistic regression is applied when our dependent variable, y, is binary, meaning it has only 2 outcomes, such as pass or fail, defective or non-defective, yes or no. What we're trying to do here is model the relationship between one or more independent variables, x, and that binary outcome. These independent variables can be continuous or categorical. Let's break this down. Use this test when your y variable is binary and your x variable is continuous. Example: whether a product passes a quality check, y, based on the number of training hours completed by the operator, x. Now in terms of hypotheses, O null hypothesis, H0, x does not significantly affect y. O alternate hypothesis, HA, x does significantly affect y. This is where p-values help us decide which hypothesis is likely to be true. Let's take an example. Suppose we are trying to predict whether a product will pass or fail the final inspection. Why? And we believe that the tenure of associates, Rx, may be impacting this. By using binary logistic regression, we can quantify the likelihood that a longer or shorter tenure influences quality outcomes. So, in summary, binary logistic regression helps us estimate the probability of a binary event happening, using predictors that may be continuous or categorical. It's powerful in quality checks, HR assessments, and any process improvement initiative where binary outcomes matter. Let's take a moment to clearly define what binary logistic regression is and when we use it. Binary logistic regression is a predictive analysis technique that helps us explore the relationship between one or more independent variables, which can be continuous or categorical, and a binary dependent variable. Binary means there are only two possible outcomes, such as pass or fail, defective or non-defective, 0 or 1, yes or no. So, when should we use binary logistic regression? First, it's the go-to method when the outcome variable is binary. It allows us to predict the probability of success or failure, which is extremely valuable in operational, manufacturing, and service environments. It also helps us understand which factors significantly influence the result, which can inform decisions, root cause analysis, and process improvements. For example, in quality control, it could be used to predict whether a product will fail inspection based on machine settings, operator experience, or shift timings. In customer service, it can help predict customer churn, whether a customer will stay or leave based on engagement metrics. In predictive maintenance, we can estimate the likelihood of a machine failing based on sensor readings or usage data. So, in short, binary logistic regression is your tool when you have a binary outcome and want to model or influence that outcome using meaningful predictors. As we begin working with binary logistic regression, it's very important to understand the key assumptions that must be met for the model to be valid and reliable. Let's walk through them one by one. Assumption 1. Dependent variable is binary 0 or 1. This is fundamental to logistic regression. Your outcome variable must have only two possible values. For example, pass, fail, yes, no, churn, stay, or defective, she, not defective. Assumption 2. Predictors can be continuous, categorical, or both. One of the strengths of logistic regression is its flexibility. Your input variables, or predictors, can be numeric, like age, tenure, categorical, like department, shift, or even a mix of both. Assumption 3. Observations are independent. Each observation or record should be independent of the others. If there is correlation between records, e.g., repeated measures from the same individual, then logistic regression is not appropriate without accounting for that. Assumption 4. No perfect multicollinearity between predictors. Predictors should not be highly correlated with one another. Multicollinearity can distort the coefficients and make the model unstable. It's good practice to check correlation, or VIF, variance inflation factor, before finalizing your inputs. Assumption 5. Linear relationship between continuous predictors and the logit of the outcome. This is a bit technical. While logistic regression doesn't assume a linear relationship between the independent variables and the outcome directly, it does assume linearity between continuous predictors and the log odds, log IT, of the outcome. In summary, if these assumptions are violated, the reliability of your logistic model may be compromised. So before fitting the model, it's a good idea to check these assumptions carefully. Let's now look at an actual example of a binary logistic regression output and understand how to interpret it step by step. Context of the analysis. We're trying to model a binary outcome, likely something like pass versus fail, and we are testing whether two predictors influence this outcome. 1. TOS, type of service. 2. Average payment size key output. Sections to discuss. P-value for overall model. At the bottom, the test of all slopes gives us a p-value equals 0.003. This tells us that at least one predictor significantly impacts the binary outcome. We can reject the null hypothesis that all slopes are 0. Individual predictors. 1. TOS. O coefficient equals 0.0185. P-value equals 0.0310. Since the p-value is less than 0.05, this predictor is statistically significant. O positive coefficient means, as TOS increases, the odds of the event, pass, increase. Average payment size, O coefficient, equals negative 0.0181. P-value equals 0.0120 again. The p-value is significant, and the negative sign indicates that higher average payments are associated with lower odds of success. Pass. Interpretation. Tip: in logistic regression, the coefficients impact the log odds. So, a positive coefficient increases the likelihood of the event, and a negative coefficient decreases it. Summary: this model is statistically significant overall, and both predictors, TOS and average payment size, are individually significant. The analysis helps us conclude that these factors influence the probability of a successful outcome. Let's now go over how to interpret the results of a binary logistic regression in a step-by-step manner. Step 1. Start with the overall p-value. The first thing to look at is the p-value given below the regression table, which tests whether at least one of the predictors significantly affects the outcome. If this p-value is less than 0.05, we reject the null hypothesis and accept that at least one predictor significantly impacts y. Step 2. Look at p-values of individual predictors. Now, look at the p-values for each factor, like TOS, or average payment size in our earlier example. If a factor's p-value is less than 0.05, it significantly impacts the binary outcome. If it's greater than 0.05, we assume it does not have a significant effect. Step 3. Understand the regression equation. We use the model's coefficients to construct a regression equation. Y equals constant plus coef. 1 times factor 1 plus coef 2 times factor 2. In our example, y equals 0.55634 plus 0.0185200 times TOS 0.0182121 times average payment size. Step 4. Interpret the coefficients. Positive coefficients mean higher values of the factor increase the odds of the event, e.g., pass. Negative coefficients mean higher values reduce the likelihood of the event. Coefficients close to 0 indicate little to no impact. Step 5. Check the odds ratios. Finally, interpret the odds ratios. An odds ratio greater than 1 implies an increase in the probability of the event. An odds ratio equal to 1 means no effect. Less than 1 means reduced likelihood of the event occurring. In summary, always move from the overall model significance, then to individual predictors, and finally interpret the direction and strength of those predictors through coefficients. Let's now look at ordinal logistic regression, a powerful statistical tool used when the outcome or dependent variable is ordinal. That is, it has a natural order or ranking, but the intervals between categories are not necessarily equal. What is ordinal logistic regression? Ordinal logistic regression helps us understand the relationship between one or more independent variables, which can be continuous or categorical, and a dependent variable that is ordinal. For example, survey responses like extremely satisfied, satisfied, neutral, dissatisfied, extremely dissatisfied. When to use ordinal logistic regression. When Y is ordinal and discrete, like satisfaction level or pain scale. X is continuous, e.g., age, income, or can also be categorical. Hypothesis testing. We test two hypotheses. Null hypothesis, H0. X does not significantly impact Y. Alternate hypothesis, property, X significantly impacts Y. If the p-value is less than the significance level, commonly 0.05, we reject the null hypothesis. Real-world example. A good example is analyzing customer satisfaction, CSAT. Let's say your outcome is the level of satisfaction, ranging from extremely dissatisfied to extremely satisfied. You want to see if that level is impacted by age. Ordinal logistic regression helps identify if age has a statistically significant effect on satisfaction ranking. In summary, use this model when you're working with ordered categories and want to quantify the influence of predictors on those ranked outcomes. Let's understand what ordinal logistic regression is and when we should consider using it. What is ordinal logistic regression? Ordinal logistic regression is a predictive statistical technique used when we have one or more independent variables, which can be either continuous, like age, income, or categorical, like region, department, and a dependent variable that is ordinal, meaning the outcome categories have a clear order but not necessarily equal spacing between them. Examples of ordinal outcomes include satisfaction levels, very dissatisfied to very satisfied, performance ratings, low, medium, high, or risk levels, low, moderate, high. When do we use it? We apply ordinal logistic regression when our dependent variable has ordered categories. We want to predict the likelihood of a response falling into a higher or lower ordered category. We want to identify which predictors significantly influence whether the response falls into those higher or lower categories. For instance, we might want to see how years of experience, training hours, and job role impact employee satisfaction, rated on a 1 to 5 scale. This technique is valuable in cases where the nature of the outcome is ranked, but the distance between ranks isn't uniform. Perfect for survey and service quality analysis. Before we apply ordinal logistic regression, it's important to ensure that the following key assumptions are met. Let's walk through them one by one. 1. Dependent variable is ordinal. This is the foundation of this model. The outcome variable must be ordinal, meaning it reflects a natural order, such as satisfaction ratings, low to high, or agreement levels, strongly disagree to strongly agree. However, these categories don't need to be evenly spaced. 2. Independent variables can be continuous or categorical. You can include age, income, or scores, continuous variables, or department, location, or gender, categorical variables, as predictors in your model. The flexibility here is useful across different datasets. Third, observations are independent. Each observation must be statistically independent of the others. That means the response from one subject should not influence or depend on the response of another. Violating this could bias the regression results. Fourth, proportional odds assumption or parallel lines assumption. This is unique to ordinal logistic regression. It assumes that the relationship between the independent variables and the odds of being in higher versus lower response categories is the same across all category thresholds. In simple terms, the effect of each predictor is consistent across the response levels. If this assumption doesn't hold, the model may not be appropriate, or you might need to use a more flexible model like generalized ordered logistic regression. Ensuring these assumptions are satisfied allows us to make valid inferences from our ordinal logistic model. Let's now look at how to interpret the results of an ordinal logistic regression using the example shown on the screen. First objective. We are trying to understand if the predictor variable TOS, tenure of service, significantly affects the grade, which is our ordinal dependent variable with categories excellent, good, and fail. 2. Focus on the overall model p-value. At the bottom, we see a test result that reads p-value equals 0.584 for the test that all slopes are 0. This is the overall model test. Since 0.584 is greater than 0.05, we fail to reject the null hypothesis, meaning TOS does not significantly influence the grade. 3. Check the individual predictor .TOS. In the regression table, we also look at the row for TOS. Coefficient 0.004, 7503. P-value 0.602. Again, this is much higher than 0.05. This confirms that TOS is not a statistically significant predictor of the grade. 4. What does this mean? The odds ratio is 1.00, indicating no change in odds for a unit change in TOS. This tells us that tenure doesn't help us distinguish between someone being in the excellent, good, or fail category. 5. Takeaway. Message. Always begin with the overall model test. If that's not significant, your model may not be helpful. Then check individual predictors, both their p-values and odds ratios, to understand if and how they impact the ordinal response. If the assumptions are satisfied but the predictors aren't significant, consider checking other predictors or reassessing model fit using alternative data. Now let's understand how to interpret the results of an ordinal logistic regression model. Step 1. Start with the overall p-value. Begin by locating the p-value shown at the bottom of the regression output. This value tells us whether the model as a whole is statistically significant. If the p-value is less than 0.05, the commonly used alpha value, we reject the null hypothesis. This means that at least one of the predictors significantly impacts the ordinal dependent variable. Step 2. Check individual predictor significance. Next, review the p-values for each predictor or factor included in the model. If multiple predictors are used, each will have its own coefficient and p-value. A predictor is statistically significant if its p-value less than 0.05, meaning it significantly impacts the ordinal response. Step 3. Understand the structure of OLR. Ordinal logistic regression. OLR is different from binary logistic regression because it uses multiple logistic equations to estimate the probability of the response falling into one of several ordered categories. These equations allow us to calculate cumulative probabilities for each threshold in the ordinal outcome, like satisfied, neutral, dissatisfied. Final tip: remember, just because the overall model is significant doesn't mean every predictor is. Evaluate both the model and individual predictors to derive meaningful insights. Let's now explore nominal logistic regression, which is used when our dependent variable is nominal, meaning the categories do not have any natural order. For example, types of vehicles, colors, customer complaint types, etc. When to use it? We apply nominal logistic regression when O, the Y variable, is discrete and nominal, such as car model, customer type, or issue type. O, the X variable, is continuous, like age, income, or time. This model allows us to understand if and how the independent variable influences the likelihood of each nominal category. Null and alternate hypotheses. H0, null hypothesis. The predictor x does not significantly impact the outcome. Y. Alternate hypothesis. The predictor ux does significantly impact the outcome y. Example. Consider a car company trying to determine if car variant preference is influenced by the age of the customer. The car variant is nominal, SUV, sedan, hatchback, while age is continuous. Using nominal logistic regression, the company can understand if younger customers prefer a different variant compared to older ones. This form of regression is especially helpful in marketing, product design, and consumer behavior analysis, where we need to understand category preferences based on influencing factors. Let's take a look at what nominal logistic regression is and when we use it. What is nominal logistic regression? Nominal logistic regression is used when the dependent variable is categorical with more than two levels, and these categories do not follow a natural order. Examples of such variables could include customer complaint types, product variants, preferred payment modes. These are names or labels and not ranked or ordered. When do we use it? We use nominal logistic regression when the dependent variable has three or more unordered categories. We want to understand how one or more independent variables, x, impact the probability of the outcome falling into each of these nominal categories. Our goal is to identify which predictors significantly influence the classification or selection among the categories. This model is very useful when you're working on marketing studies, customer choice modeling, or healthcare diagnosis classification, where the outputs are labels and not ordered scales. It's important to remember that nominal logistic regression builds a set of equations for each category and compares them against a reference group. Let's now talk about the key assumptions of nominal logistic regression. These are important to ensure the validity of the results. Assumption 1. Dependent variable is nominal. The dependent variable must be nominal, meaning it consists of categories with no natural order. For example, product type, job roles, or customer preferences. Assumption 2. Independent variables. The predictors or independent variables can be either continuous, like age, income, or categorical, like gender, department. Assumption 3. Independent observations. All the data points must be independent of each other. There shouldn't be repeated measures or paired data unless adjustments are made. Assumption 4. No multicollinearity. There should be no multicollinearity among the independent variables. That means predictors shouldn't be highly correlated with each other, as this can distort the interpretation of the model coefficients. Assumption 5. Sufficient sample size. Finally, we need a reasonably large sample size to ensure stable and reliable estimates. Ideally, each category of the dependent variable should have enough representation. Remember, violating these assumptions can lead to incorrect conclusions, so it's always best to check them before running the model. Now, let's interpret the results of this nominal logistic regression output, where we're analyzing how price impacts color choice, with yellow as the reference category. Step 1. Look at the reference category. The model compares each other category of the response variable to the reference, which in this case is yellow. So we are analyzing Logit 1, red versus yellow, Logit 2, black versus yellow. Step 2. Focus on the p-values. Let's check the p-values of the predictor price. For Logit 1, red chart yellow, the p-value is 0.042. For Logit 2, black chio yellow, the p-value is 0.0322. Black chio yellow, the p-value is 0.011. Since both p-values are less than 0.05, we conclude that price significantly influences the customer's choice of color. In simple terms, the cost of the car impacts whether customers pick red or black over yellow. Step 3. Coefficients. A positive coefficient would suggest that as the price increases, the log odds of choosing that color over yellow increase. A negative coefficient, as we see here, implies that higher price reduces the likelihood of choosing red or black over yellow. So in this example, as price increases, customers are less likely to choose red or black compared to yellow. Final takeaway. This model helps us understand how predictors, like price, affect category choices without any natural order. It is especially useful in marketing, consumer behavior, and product design decisions. Let's now understand how to interpret the output of a nominal logistic regression. Step 1. Start with the overall p-value. At the bottom of the output, you'll usually see a p-value for the overall model. If this p-value is less than 0.05, it means the model is statistically significant. At least one of the predictors is influencing the response variable. This allows us to reject the null hypothesis and accept the alternate that X significantly impacts Y. Step 2. Analyze each predictor. Once we know the model is significant, we examine the individual p-values for each predictor, or factor. Look at the p-values next to each predictor. If p is less than 0.05, that predictor significantly influences the choice among the categories of the response variable. If you're using multiple predictors, this step becomes even more crucial for identifying which variables matter most. Step 3. Understand model construction. Nominal logistic regression doesn't predict a single outcome like binary logistic. Instead, it uses multiple logistic equations, one for each category compared to a reference category. These parallel equations help assess how the independent variables affect the odds of choosing one category over another. Example scenario. Suppose a car company is trying to understand how price influences the choice of car color. NLR helps us analyze whether higher or lower prices lead to a greater probability of choosing red over yellow or black over yellow. This model is particularly useful in marketing segmentation, consumer behavior analysis, and classification problems where there are multiple non-ordered outcomes. This slide provides a comparative overview of the three types of logistic regression models: binary, ordinal, and nominal, based on the type of dependent variable, y, and the nature of predictors, x. 1. Binary logistic regression. When to use binary logistic regression when your y variable is discrete and binary, for example, pass or fail, yes, no, or 0, 1, and your x variable is continuous. Hypotheses: null, ho, x does not significantly impact y, alternate. Ha, x significantly impacts y. Example: we can test if employee tenure impacts pass, CHOF, fail outcome of quality checks. Second, ordinal logistic regression. When to use this model when your y variable is ordinal, e.g. ratings like satisfied, neutral, dissatisfied, and x is continuous. Hypotheses: oh-ho, x does not significantly impact y, oh-ha, x significantly impacts y. Example: use it to evaluate whether the age of a customer account impacts their CSAT rating on a scale from extremely dissatisfied to extremely satisfied. 3. Nominal logistic regression. When to use, apply this when your y variable is nominal, e.g. car type, color choice, with no natural order, and x is continuous. Hypotheses: oh-ho, x does not significantly impact y, oh-ha, x significantly impacts y. Example: a car company wants to assess if the customer's age influences their choice of car variant. This table is extremely useful for deciding which regression model to choose, depending on the nature of the outcome variable. Keep this in mind when framing your analysis in projects, especially during the analyze phase of a Six Sigma DMA project.